Chapter 12, Matter. This lecture will help you understand how to describe the properties of liquids and gases and to solve density and specific gravity problems. A liquid is a substance that has a definite volume and takes the shape of its container. Liquids are incompressible. The molecules move in a flowing motion, yet are so close together that it is very difficult to compress a liquid. Properties of liquids are cohesion, adhesion, surface tension, viscosity, and capillary action. Cohesion is the action or property of like molecules sticking together. Cohesion means sticking together. There is a force of attraction between molecules in liquids. Below the surface of the liquid, the force of cohesion between the molecules is the same in all directions. Adhesion is the tendency of dissimilar particles or surfaces to cling to one another. When the force of adhesion is more than half as large as the force of cohesion between the liquid molecules, the liquid is said to wet the solid. In the case of water, its adhesive forces are greater than its cohesive forces. Put a glass in water and pull it out, some water remains on the glass. The force of adhesion between paper and water combined with the force of cohesion between water molecules explains why sheets of paper stick together. In the case of mercury, the opposite is true. Mercury's cohesive forces are greater than its adhesive forces. If glass is submerged in mercury, then pulled out, virtually no mercury remains on the glass. Molecules on the surface of the liquid, however, feel a net force of attraction that pulls them back into the body of the liquid. As a result, the liquid tries to take on the shape that has the smallest possible surface area, the shape of a sphere. The magnitude of the force that controls the shape of the liquid is called the surface tension. The stronger the bonds between the molecules in the liquid, the larger the surface tension. Surface tension is a result of cohesive forces between adjacent molecules. The molecules in the bulk of the liquid are pulled equally in all directions by the neighboring molecules, but the surface molecules do not have molecules on all sides. Hence, they are pulled inwards, causing the liquid to shrink to form a surface with minimum area, a sphere. Hence, water droplets are spherical. Water molecules beat together on a leaf because surface tension is greater than the adhesive forces between the leaf and the water molecules. The surface tension of water allows objects heavier than it to float across it. When water molecules do not stick together, the object is non-wettable, and the weight of the object is less than the forces due to surface tension. The ability of the surface of water to support a needle is an example. On the left, the water surface acts like a thin, flexible surface film. The surface tension of water can be reduced by adding soap to the water. On the right, soap is added to the water to decrease the surface tension of the water, and the needle sinks. Soap is added to laundry so that the water more easily penetrates the fibers of the clothes being washed. Viscosity is a measure of the resistance to flow. Motor oils are more viscous than gasoline, for example, and the maple syrup used on pancakes is more viscous than the vegetable oils used in salad dressings. If a liquid's temperature is increased, its viscosity decreases. Capillary action is the ability of a liquid to flow in narrow spaces without the assistance of and in opposition to external forces like gravity. The effect can be seen in the drawing up of liquids between the hairs of a paintbrush, in a thin tube, in porous materials such as paper, in some non-porous materials such as liquefied carbon fiber, or in the cell. It occurs because intermolecular forces between the liquid and the surrounding solid surfaces. If the diameter of the tube is sufficiently small, then the combination of surface tension, which is caused by cohesion within the liquid, and adhesive forces between the liquid and container act to lift the liquid. Plants use water to keep their roots, stems, leaves, and flowers healthy as well as prevent them from drying and wilting. The water is also used to carry dissolved nutrients throughout the plant. Most of the time, plants get their water from the ground. This means it has to transport the water from its roots up and throughout the rest of the plant. How does it do this? Water moves through the plant by means of capillary action. Capillary action occurs when the forces binding a liquid together, cohesion and surface tension, and the forces attracting the bound liquid to another surface, adhesion, are greater than the force of gravity. Capillary action is the property of a liquid to rise in capillary tubes they tend to wet, and are depressed in tubes they tend not to wet. Elevation or depression in the tube is inversely proportional to the diameter of the tube. The elevation or depression decreases as the temperature increases. The meniscus is the curve in the upper surface of a liquid close to the surface of the container or another object, caused by surface tension. It can be either convex or concave, depending on the liquid and the surface. The concave meniscus, as seen on the left, occurs when the particles of the liquid are more strongly attracted to the container than to each other, causing the liquid to climb the walls of the container. The cohesive forces between the liquid are less than the adhesive forces between the liquid and the container. The surface curves up, for example, water in a glass container. A convex meniscus, as seen on the right, occurs when the particles in the liquid have a stronger attraction to each other, cohesion, than to the material of the container, adhesion. When the cohesive forces between the liquid molecules are greater than the adhesive forces between the liquid and the walls of the container, the surface of the liquid is convex. Convex menisci occur, for example, between mercury and glass in barometers and thermometers. When both adhesive and cohesive forces are equal, the surface is horizontal. For example, distilled water in a silver vessel. Particles in a gas are well separated with no regular arrangement, can move past one another, and vibrate and move freely at high speeds. Gases assume the shape and volume of its container, but because of the free space between the particles, are easily compressible. Properties of gases are expansion and diffusion. Expansion is the property of a gas in which rapid movement of its molecules cause the gas to completely occupy the volume of the container. We consider two identical glass bulbs connected by a valve. Gas occupies the bulb on the left. The bulb on the right is a vacuum. When we open the valve, the gas spreads out to occupy both bulbs. Diffusion refers to the process by which molecules intermingle as a result of their kinetic energy of random motion. If you remove the cap from a can of gasoline, you soon smell the fumes. The air molecules and the gasoline molecules mix throughout the room because of diffusion. Density is an important property of all materials, solids, liquids, and gases. Density is a measure of compactness, or how much of volume an object occupies. Density also measures the lightness or heaviness of materials of the same size. There are two ways to define density: mass density and weight density. Mass density is the mass of an object divided by the volume the object occupies. Mass is measured in grams or kilograms, volume is measured in cubic centimeters or cubic meters, and the units of mass density are kilograms per cubic meter or grams per cubic meter. An example, the density of mercury is 13.6 grams per cubic centimeter. So mercury has 13.6 times as much mass as an equal volume of water, which has a density of 1 gram per cubic centimeter. Weight density is the weight of an object divided by the volume the object occupies. Weight is measured in pounds, and volume is measured in cubic feet. The units of weight density are pounds per cubic foot. Example, the density of salt water is 64 pounds per cubic foot, which is more dense than fresh water with a density of 62.4 pounds per cubic foot. For comparison, the densities of styrofoam, glass, and steel are shown. The table shows the density of various substances. Find the mass density of a ball bearing with a mass of 22 grams and a radius of 0.875 centimeters. The radius of the ball bearing is 0.875 centimeters. The ball bearing is a sphere, and the volume of a sphere is 4/3 times pi times the radius cubed, giving 2.81 cubic centimeters. Since the mass is 22 grams and the volume is 2.81 centimeters cubed, the density is 7.83 grams per cubic centimeter. The specific gravity of any material is the ratio of the density of the material to the density of water. The density of iron is 7,830 kilograms per cubic meter. Find its specific gravity. Specific gravity of iron is the density of iron divided by the density of water. The answer is 7.83. Since the specific gravity is a ratio, it does not have units. A hydrometer is a sealed glass tube weighted at one end so that it floats vertically in a liquid. Hydrometers are commonly used to measure the specific gravities of liquids. It sinks in the liquid until it displaces an amount of liquid equal to its own weight. The density of the displaced liquids are inversely proportional to the depth at which the tube sinks. That is, the greater the density of the liquid, the less the tube sinks. The less the density of the liquid, the more the tube sinks. A hydrometer usually has a scale inside the tube and is calibrated so that it floats in water at the 1 mark. Anything with a specific gravity greater than 1 sinks in water. A substance with a specific gravity less than water floats in water. Its specific gravity indicates the fractional volume that is under water. Hydrometers are commonly used to measure the specific gravities of battery acid and antifreeze in radiators. Specific gravity changes with temperature. The table gives a specific gravity of a lead acid battery and antifreeze at various temperatures. The following are a set of problems for you to work on. Pause the video to give yourself time to work on the problems. A packing crate of dimension 2.50 meters by 0.80 meters by 0.45 meters weighs 1.41 times 10 to the 5 newtons. Find the stress in kilopascals exerted by the crate on the floor in each of its 3 possible positions. Pause the video to work on the problem. The box has 3 faces, each of different area. The first, the side with an area of 2.5 meters by 0.8 meters, is calculated. The total stress is 71 kilopascal. The second face has an area of 1.2 meters by 0.45 meters, and the stress is 130 kilopascal. The third face is 0.4 meters by 0.8 meters, and the stress is 390 kilopascals. What is the original length of a spring with spring constant 96.0 newtons per meter that is stretched to 28 centimeters by a 15 newton weight? Pause the video to work on the problem. The total length of the spring when stretched is 28 centimeters. We are interested in the length of the stretch, delta L, but do not know the unstretched length that we call X. Using the known applied force of 15 newtons and a spring constant of 96.0 newtons per meter, the change in the length is 0.156 meters. If the stretched length is 0.280 meters, the unstretched length is 0.280 meters minus 0.156 meters, or 12.4 centimeters. What size tank in liters is needed for 1,000 kilograms of A, water at 1,000 kilograms per cubic meter, B, gasoline at 6,800 kilograms per cubic meter, and C, mercury, 13,600 kilograms per cubic meter. Pause the video to work on the problem. We are interested in the volume of the container that can be found using the definition of density as the basic equation. Solving for the volume gives us the working equation. The volume needed for 1,000 kilograms of water is 1,000 liters, using that 1 cubic meter is exactly 1,000 liters. The volume needed for 1,000 kilograms of gasoline is 1,470 liters. The volume needed for 1,000 kilograms of mercury is 73.5 liters. Your assignments are to read Chapter 12 in the textbook. Your homework assignments are due April 13th.